Let's take a look at how we represent information using these zeros and ones, these low voltages and high voltages. We're going to group our binary digits, bits, into groups of 8 that we're going to call bytes. And if we do that, you'll notice that we can have a range of values that go from 000 to 11111. And that gives us a range for the kinds of numbers we can represent in a single byte. That's going to correspond to 0 decimal to 255. And how did we get that 255? Well, if we think about numbers being represented by a ones digit, and then of course in decimal we would have a tens digit here, but in binary that's a twos digit, and then a fours digit, and an eighths, and sixteens, and 32s, 64s, and 128s. So if we add all of those values, we would get 255. As a little example, let's take a look at this number here, 00101011. That corresponds to a 1 in the 32s column, a 1 in the 8s column, a 1 in the 2s column, and lastly a 1 in the 1s column. When we add those values, we get the decimal number 43. In the other direction, if we started with the number 26 in decimal, that's a 16 plus an 8 plus a 2, all powers of 2. And that yields the following binary number, 00101010. So the conversion is pretty simple. It pretty much involves just the powers of 2. Now, one of the things that we do, because it gets tiring to say 00101010, we'll take a byte and represent it as 2 hexadecimal digits. Hexadecimal digits are base 16 digits. So now instead of a ones column or a twos column, we have a ones column and a 16s column. So in this case, we would represent a byte by the digits 00. Each one of these is a group of 4 binary digits, and we can range all the way up to FF, the case of all 1 binary digits like we had above. The table on the right shows you the correspondence of the numbers from 0 to 15 in both binary and hexadecimal. So you can see that we use the numbers 0 through 9 because we're already familiar with those. We use this in our decimal system, but those other 6 values we need from 10 to 15 in base 16, we'll use the letters A through F. And the correspondence to the binary digits is right here. So we can see we go from the initials all zeros to a final all ones. Okay, in the C language, we can write these expressions, these values very easily by using the notation 0x to indicate a hex number, a number in base 16. Here we see an 8-digit hexadecimal number. Since the digits are 4 bits each, that's a 32-bit long number that will be represented in 4 bytes. And in C, it doesn't matter whether we use uppercase or lowercase letters. Either one will work. Okay, so now that we have an idea of how the numbers are represented, and we'll be going a lot more into that soon, but we have our basic integers here. How do we find these in memory? So the first thing we should understand is that memory has been organized also in bytes. Basically, it's just a big long list of bytes. And each one of these bytes has an address or an index that we can use to refer to it. We start at the index that begins with all zeros, and we end at the index of all ones, or all Fs in hexadecimal notation. All right, so basically we have a byte at the start, followed by another byte, another byte, another byte, all the way to the end. How many bytes do we have? Well, that depends on how many bits we have in the address. That's possible. And we're going to see that we have 32-bit machines that use 32-bit addresses, and the more modern 64-bit machines that use 64 bits of address. right? Where do those numbers go in these little bytes in memory, these locations, is dependent on the compiler and the runtime system of our machine. It will decide where the various numbers are stored and allocates them by finding a place for them in that memory. All right, so let's talk a little bit about machine words. I've been mentioning that maybe we'll have machines with 32-bit addresses or 64-bit addresses. That amount corresponds to the word size of the machine. The word size is also the nominal size of all the integer values we use. So in a 32-bit machine, we'll have integers that can go up to 32 binary digits. And this includes addresses represented in words. So as I mentioned before, until recently, most machines use 32 bits or 4-byte words. In the old days, we also had machines with 16-bit words, or even at the very beginning, 8-bit words. This limits addresses to 4 gigabytes. That's how many different numbers we can have in 32 bits. Therefore, how many different addresses that we can have in the memory. This has become now too small for many memory-intensive applications. Many of our applications use much more space than that. So computers have changed to use 64-bit words, 8 bytes long. And now we can have 2 to the 64 different addresses, which leads to 18 exabytes of data to be addressed. That's a huge amount, and we haven't run into that wall yet, but we probably will one day. So for backward compatibility, though, many CPUs still support different word sizes. We'll be looking primarily at 64 and 32 bits, but there are some instructions that you'll encounter that might manipulate 16-bit quantities or 8-bit 1-byte quantities. All right, so how do we refer to then to these larger things in memory? We have mentioned bytes so far. Well, that's what we see here on the right in this slide. We have an address corresponding to each byte of the memory, each individual little cell where we can put an 8-bit quantity. But I just said that we use 32-bit words to represent numbers in many of our machines, so 4 bytes will have to be grouped together to represent a single word. Well, what address are we going to give that word? The next one after it will also require an address. What will we use for that? In a 64-bit machine, of course, we'll have to group the first 8 bytes into a word. And then we have to decide on the address for that. To have a uniform policy, what we do is we say the address of the word is the address of the first byte in the word. So in this case, we would have the first 32-bit word would have the address 000 because it starts at that byte. The next word's address, though, is 0004. And it doesn't make any sense to talk about the words between those at addresses 1, 2, and 3 because we're going to be grouping things in this 4-byte structure. So we want to move on to the next 4-byte structure. So the next address will be 4, the next address will be 8, the next address after that will be 12, and so on. And these are in base 10.